In this series of videos, we're going to look at section 4 of unit 9, which is looking at how we can represent functions using power series. So in the previous section, we reviewed what we knew about interval and radius of convergence of power series. That was also something that we looked at in our chapter on just series convergence or divergence. So now, to be able to write these Taylor polynomials, sometimes it's not very easy to come up with a format that is easy to work with. We want to create these power series, okay? So the easiest way to do this when you can, it doesn't always work, but is to use the geometric sum formula to write it in the form of a geometric power series. And the reason why that is helpful is because remember that the sum formula for a geometric power series is A over 1 minus R. Okay, that's how we find the sum when you have a series of the form sum from 0 to infinity of A times R to the n power. That's where the A and the R are coming from. Remember that with geometric, in order for this sum formula to work, your series must start at 0. Okay, it can be geometric if it starts somewhere else, but the sum formula only works if it starts at 0. Okay, so for a first example here, let's look at this function f of x equals 1 over 1 minus x. This looks pretty close to following that pattern of A over 1 minus R. In fact, this one pretty much follows that pattern exactly. So we can notice that if we match these two things together, A over 1 minus R, A over 1 minus R, we can see that in this case, 1 is in the position where A was, and X is in the position where R was. So we can take that information and plug it into this general formula here, and it would become 1 times X to the n power, because that's our A and that's our R, and that's how we end up with this general definition of this series here, which we can write out as a polynomial in this form. Now, this statement here that the absolute value of x has to be less than 1, that's the rule for convergence of a geometric series, is that, remember, in general, the absolute value of your ratio must be less than 1. That's a special case of the ratio test. So that's what that statement is there. So it's only going to represent that series, f of x equals 1 over 1 minus x, on that particular interval from -1 to 1. And it cannot include the endpoints because it will not converge. So it doesn't quite represent f of x all of the time. So we have to write a different series if we want to look at a different interval. So this is where we end up having to do a little bit of fancy algebra, which is always, my favorite part of everything. So if we want to center it at -1, for example, then we need to change the value of x. Okay, it was just at 1 minus x because our center was 0. If I want to change the center to -1, remember that that has to be in the form of x minus c. So x minus -1 is why this becomes x plus 1. Okay, now we have to do a little bit of magic to get that into this form of A over 1 minus R. Okay, and so what we did here on this example is a couple of things to start. The biggest thing, and the place where I always like to start first, is that we need this to be a 1. And so the first thing that we did was noticing that here it was a 2. We went through and divided the top by 2 and divided everything in the bottom by 2. That's essentially the same as multiplying by 1/2 over 1/2, which is just 1. That's why we're allowed to do that. Let me take this out right here. So that's what we did. That's how we end up with 1/2 on the top here. And then now we have 1 because 2 divided by 2. And we end up with x plus 1 over 2 there. So now you can see that in this form, a is equal to 1/2 and r is equal to x plus 1 over 2. And if we put that into the a times r to the n format, you can see that this is the series that we get. This is, I think this is a typo. This is copied straight out of our book, but that's not correct. This should be the series for when it's centered. Oh, well, no, it is true, but the note here is that this is when it is centered at c equals -1. Okay, so both of these series are representations of 1 over 1 minus x, the one we did at the beginning and the one we're doing now. We've just changed the center. Okay, and then again, we know that this value has to be less than 2, and this comes from doing the ratio test and finding your interval of convergence there, okay? And so you can see when you use this information about your center and your radius that you end up having an interval from -3 to 1 where that works, and you don't end up including either of the endpoints there. So we can take a peek at these graphs here. This is what the graph of 1 over 1 minus x truly looks like, okay? And then when we take this series and choose to define it, we only end up getting this little section of the graph right here, which this does extend. I'm sorry, I'm pointing on my computer screen and you can't see that. So our interval that we just found is from -1. This is the first example that we did where it was centered at 0. It's only good from -1 to +1. This does extend infinitely this way. We saw the polynomial had infinite terms, but because of the asymptote at 1, that's why we don't end up getting anything else there, and you'll never get a number less than -1. So it's not possible for us to continue on further than that using this series, okay? That's just kind of a visual representation of what that radius of convergence is telling us. So let's look at an example then where we can work this through ourselves. So we want to find a power series for f of x equals 4 over x plus 2 centered at 0. So we don't have to do anything weird with the center. But we can see that we have sort of those 3 pieces, a over 1 minus r, even though we're not quite in that form yet. So we're going to have to start manipulating. So the first thing that I usually do to start these is to get all my pieces in the right spot. So I'm going to start by switching the order in the denominator. Whoops, I didn't do it. So I have 2 plus x because I know that that x needs to be in the r spot. Now what I'm going to do, because again, like I said, I always start by tackling this first. I need that to be a 1. So I'm going to multiply again by 1/2 over 1/2, which is really just 1. So we're allowed to do that. And that gives us now 2 over 1 plus x minus 2. And so that's real close. The only thing that's not matching right now is that we need this to be a minus. And so sort of the little algebra trick that we use is the idea of subtracting a negative, giving us a positive. So I can rewrite this as 2 over 1 minus negative x over 2. And you can see that's still equivalent. But now I have this in the form that I want, which is a equals, or a over 1 minus r. And so all of those pieces now fit together, okay? So we can see that from all of this information, now we know that we need a to equal 2 And we need r to equal negative x over 2. Oops, that's a 2. So that takes us then to our power series. We want to set this up from n going from 0 to infinity for our summation. We need a times r to the n. So that's going to be 2 times negative x over 2 to the nth power. Now, we know that when we have that alternating bit, it's kind of helpful to write it out separately. So I went ahead and wrote it this way as the sum from n equals 0 to infinity of negative 1 to the n. That's basically pulling out just this part to the n, times 2 times x over 2 to the nth power. That looks a little bit nicer. Now, as a general habit here, we now want to list this out in its polynomial form, and we want to also include the general term when we do that. So if we just start from the beginning and plug in values for n. So when n is equal to 0, x over 2 to the 0th power is just 1. Negative 1 to the 0th power is 1. So we're just left with 2. Plus, when we do to the first power, well, we won't actually have a plus. To the first power is going to make this negative 1 to the first, times 2 times x over 2. So the 2's cancel and we just get minus x. Plus, because the next one is negative 1 squared, we're going to get 2 times x squared over 4, which is going to make this x squared over 2. And I don't quite see a pattern just yet, so I'm going to go ahead and do one more. The next one will be negative x to the third over 4. And now I am kind of starting to see that pattern that when I do the squared power, because I am multiplying by this 2, it always ends up doing one less. So like here, this is 2 to the first. Here, this is 2 to the second. So it's one less than the term number that we are on. And so we're going to say plus dot, 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 plus our general term, which is going to be, remember it alternates, and then we definitely have x to the n. That term stays the same. But the power below ends up being 2 to the n minus 1. And then plus dot, dot, dot on to infinity. But we want to give that general term. So now if I said like, what's the 37th term? You'd be able to just plug in 37 and figure out what that term was going to be. Okay? And so there it is. There's our power series centered at 0. Now, based on what we know about power series, we know that the absolute value of x over 2 has to be less than 1 in order for that to converge. If it was asked for, you could then go forwards and go ahead and figure out what the radius, well, we know what the radius is, but what the interval of convergence and all of that good stuff is from there. But that's a good place to start. Okay. Now there is another example very similar to this one. So I'm going to suggest that you go ahead and put the video on pause and try this one out on your own. I'm going to put the work up here in just a magic moment. But go ahead and try this one so that you can see kind of if you're on the right track. Here's a hint to get you started. Because we have 1 over x, we don't have that 1 minus r pattern on the bottom. So in order to get a 1 in there, I went ahead and used this trick of adding 0. 1 minus 1 is really 0, but that now gets me the 1 that I need. And so what I will do now is go ahead and reorganize this and rewrite it into the form that I want. And so I need to keep that minus, but I can't just stick parentheses around that right there without factoring out the negative. And that's not going to be very helpful because then I have 1 minus x, but we can adjust for that in a different way. So here's how I did that. What I did here was I went ahead and factored out the negative from this. So that gives me 1 minus 1 minus x. But because this is not in the form that we want of x minus c, in order to reverse that, I need to factor out a negative again, but I don't want to lose this negative, so I'm going to factor out just inside the parentheses, which gives me 1 over 1 minus negative x minus 1. And that is where you can go forward. Okay, so now those are your pieces for A and R, and see what you can do from there. Go ahead and pause it again, and I'll do the rest in a sec. And this is what you should end up with. So we have our A times R to the n power, and we can clean that up a little bit to get to here. And if you write out a few terms, you can see the pattern pretty quickly, which ends up matching the general term that we wrote down at the beginning. And then this would be the restrictions on convergence. And you can see that the way this ended up working out, which we need to make sure we double check, we can see that the center is at 1, so that matches with what we needed to have happen. You might have to do a little bit more algebra to adjust to make sure that it is centered at 1, pulling pieces apart, combining different terms and those sorts of things. So, that is how you can use the geometric sum formula to write power series if possible.